All right, students, let me try another video solution here. How about chapter 28, number 35? And it says here, a particular galvanometer requires a current of about 1.5 milliamps for full-scale deflection. Now, we haven't really dealt much with the galvanometer. We're going to be talking a little bit about it. It's kind of your standard analog instrument. It usually has a round face and kind of has a needle. You might call this like a speedometer would be a good example of a galvanometer being used to measure your speed, and it would then move along a scale. A fuel gauge, all your gauges basically are a galvanometer. And when we get into magnetism, we'll talk a little bit more about it, but basically there is a magnet, and this is where we'll talk more about the galvanometer. So there'll be a north pole to our magnet and a south pole to our magnet, and then some current comes in here and goes through some windings. And as the current goes through the windings, it creates a torque that then twists it, and then in addition to that, there's a spring connected on here, and so the needle moves over based upon when the torque from the spring pushing it back and the torque from the current going through it through the coils here near the magnet balance each other. And so if there's like a lot of current, then maybe the needle will rest equilibrium at that point. If there's only a medium amount of current, at that point, and if no current, it'd be back at that point. And so how much torque we get depends on how much current goes through there. So more on this coming up when we get into magnetism. And you don't really even need to know all that. I just thought that maybe part of this problem might be for somebody that is not knowing, well, what's a galvanometer? And, and just having a little more detailed explanation might be useful. And so if you want to flip ahead, I think it is chapter 30. It might be 29, but I think it's in 30 where they have applications of magnetism. And so we'll be there soon. And this is the galvanometer. What you need to know for this then is just that a galvanometer is a gauge. It's a gauge that moves based on how much current goes through it. And so this one is saying that this particular galvanometer requires a current of 1.5 milliamps for a full-scale deflection. So if you were to put this, current through the galvanometer, so I'll make wires coming in and wires coming out, the needle would move over to here. As I said, internally there would then be a torque between the current and the magnet, and then also the counter torque coming from the spring. And so that would make it full scale, which presumably halfway would be half that current. And so that'd be like 0.75. So at 0.75 milliamps, there would be enough current to move the needle halfway. All right, so we can go anywhere in between a zero deflection and a full-scale deflection, which means the current can go anywhere from 0 up to 1.5 milliamps, and then the dial would move. And that's really not much current, 1.5 milliamps. So it goes on to say then that it has a resistance of 75 ohms. And so maybe I'll just write that right here, 75 ohms. But to give you a little more understanding, then this galvanometer then has very thin wires coming into this coil and coming out. So they're the coils that make up the armature here of the galvanometer has a magnetic field, and there's going to be long wire because it's wrapped up and it's really thin, so it comes out to be 75 ohms. In fact, it makes me kind of wonder if I should pause and just kind of grab the textbook real quick and say, where would that be? And here's 30. So I suspect it is near the places of 30, Yeah, let's go 29. Here they talk about a voltmeter. Bummers. Okay, never mind. Somewhere coming up real soon, and I probably should move on to do the rest of the problem. Your author has a really nice picture of the internal workings of a galvanometer here, and I would have thought it was in that chapter 30, but I don't see it. Could be here in 31, but it doesn't seem appropriate. All right, well, yep, I should have never grabbed the book here. I'm not sure where it is and what chapter, and then we're getting way too far now. Anyway, somewhere in here, I'm pretty sure it's that book. Maybe it's another book. Now I'm beginning to question where it is. But sorry for the distraction. Hopefully then you get an idea that we have this current that when it's this much and it's going through this much resistance, you would get a deflection. So this says it can be used to measure the voltage of wiring with a large resistor in series with the galvanometer as suggested in active figure 28. Maybe that's it. Maybe I should have kept reading. Maybe I got too far ahead of myself thinking it was in the magnetism, but they say figure 28, 22. 28, 22, I guess 13, 18, where is number 22, 19, 20, 23. Oh, well, they don't really show the internal workings of the galvanometer, but they do show that what we need to do is hook up a resistor in series with the galvanometer here, and that's what they're talking about here. So here is going to be my gauge, and just to represent it, I'm going to say internally there is a 75 ohm resistor, and then I can hook up in series an additional resistor with it so that we get this full deflection here. The effect of this resistor, as they're saying here, let me call it capital R, the effect is to limit the current in the galvanometer when large voltages are applied. Calculate the value of this resistor that allows the galvanometer to measure voltages up to 25 volts. So in other words, if we hook up a battery here that is 25 volts, we want to get a full-scale deflection. So here's our galvanometer. No current, it would point here, and full scale over to there. So when we hook it up to 25 volts, we would want it to basically get a current of 1.5 milliamps. That's what the problem is really indicating. Because if you just didn't have this resistor R, if you just had the 25 volts and divided it by the 75, that alone would give you, this is amps, 0.333 or 330 milliamps, and that is way, way more and would, probably end up breaking the galvanometer. And so without this resistor here, you get too much current. So we want to resist the current. So again, we get this full-scale deflection. So we can think of these as being in series. So the equivalent resistance would be this R plus the 75. And so applying Ohm's law for this equivalent, we would take the voltage, 25, and divide it by R plus 75. And that would get us our current. And we want this to be a full-scale deflection, so we want this to be 0.0015 amps. So if I do it in volts and ohms, I will get amps, and so there's the 1.5 milliamps. So now it's just a matter of a couple steps of mathematics to figure out then, okay, what should be the current. So let me go ahead and take this 0.0015. Maybe I'll just bring this over and divide by 25. Then I'll just take the reciprocal of that. That should be R plus 75. So then move the 75 over and subtract off 75. And we're looking at about 16,000. And I'll just round it to 16,600. And that would be then kilo ohms. And so that's the amount of resistance you would want in a series here in order for this to work. All right. Well, hope that helped. Bye.